Welcome to this tutorial, which is going to look at particle networks, or POPs. POP stands for Particle Operator. You may have noticed that here in your network pane, one of the top level contexts is this part or particle context, and you can in fact build particle networks in here. But it's often much better to embed them here in an object network, and that's what I'm going to do. So I'm going to lay down a geometry node, dive inside, delete the file node, and then lay down a POP network. And this is a container in which we're going to build our particle network. And it's worth observing that there are a number of controls here which control how the simulation will be run. And there are some connectors which allow you to connect bits of geometry into the POP network, which can then be used for collisions or for forces and so on. And we'll see an example of that later on. So let's dive inside. A POP network won't mean anything unless we create some particles. And there are a number of different ways to create particles. There's the source POP, which creates particles from an object. There's the location POP, which creates them from a single point in space. And then you can also use a stream, which creates a continuous stream of particles with a specific density of particles per unit area. I'm going to start with a location POP, and it's worth observing too that the birth tab here is common to both the source POP and the location POP. But for the moment we're going to deal with a location POP. So the first thing we want to do is set up the point from which we're going to emit our particles. And if I press play, we can see we're already getting some particles emitted. The birth tab allows you to control how many particles are emitted and at what times they're emitted. There are two basic ways to emit particles. There's the impulse birth rate and there's the constant birth rate. Let's start by looking at impulse birth rate. So I'm going to turn constant activation to 0, which means that these particles, this birth rate, is not going to apply. Impulse activation is used to create bursts of particles. So, for example, I could have $ff equals 1 in this field here, and this will evaluate to 0 whenever the frame number isn't 1. When the frame number is 1, it evaluates to 1. In other words, this impulse birth rate will create particles at frame 1, but won't create any particles at any other frame. So if I set that to 100, we can see that 100 particles are created and they then diverge. But no more particles created. I could set it to $ff. $ff is less than 3. And now for the first 3 frames, the particles will be created and thereafter they won't be. So the impulse birth rate is evaluated, this impulse activation is evaluated at every frame, and if it evaluates to a value greater than 0, then this number of particles are birthed. Let me switch that off. The constant birth rate, which also has an activation value here, which must be set to 1 in order for particles to be birthed, determines the number of particles that are birthed every second. So in this case, I'm going to birth continuously particles, 100 new particles every second. And we can see that that works. So at frame 24, which is after 1 second, if I middle click, I should see I've got approximately 100 points. So let's have a look at the rest of the parameters here on the birth tab. Well, we've got this field here called birth group, and that allows me to place the particles that are being created into a group with the name that I provide here, in this case birth. And if I then play my simulation, we'll see that there are 471 points in total, but only 4 points in birth. And the reason for that is that by default, birth is just the group of points that have been born in this particular frame. So although we've got 471 points, only 4 new points have been created in this frame. If, however, I tick the preserve group box and then play, what this does is add the new particles to the group while preserving its existing membership. So we should find that there are 467 points in total. All of them are in this birth group. The next two parameters control life, and life determines how many seconds the particles will live for before they disappear. In this case we've got a very high value, so we're not noticing the particles disappearing. Let's reduce that down to 2 seconds, and I'm going to give it a variance of 1, which means that individual particles might have a life of just 1 second or 3 seconds. In other words, 1 second either side of the life expectancy that we've given here as 2. So let's try again, and we can see the particles dying, and we can also see that different particles have different lifespans. The final tab here, and this is also duplicated on the source POB, allows you to determine the initial velocity of the particles. Now, by default it's set to an initial velocity of 0, but a variance of 1 in each direction, which means that the initial velocity is 0, and then in each direction it can vary by up to 1 unit per second. That's why we're getting this random distribution of particles. If I reduce the variance down to, say, 0.1 and give them an upward velocity of 1, we should find that our particles shoot upwards and spread out a little bit, which reflects this variance here. I'm going to expand this network a little bit. I'm going to add a force pop, like so, and I'm going to add some noise. So we'll increase the amplitude of the noise maybe to 2, and the frequency to 3, and I'm going to increase the life expectancy here to 100, and then I'm going to add a color pop just to extend the network a little bit, and I'm going to give our nodes a color. Wait a second, I need to delete the channels here. A nice red color. So let's see what we get, and we can see that the noise is spreading the particles a little bit and that they've become red in color. And the reason I've expanded the network a little bit is to indicate a difference between how a details view works in SOPs and how it works here in a particle network. So I've got a details view here, and superficially it looks pretty like the view you might see in a SOP network. We've got our points, we have position information, some velocity information, an acceleration attribute, then there's 2 life attributes, and in fact this is the total life of the particle and how long it's lived so far. The p-state, which records the state of the particle. An ID attribute, and the reason you need an ID attribute is because the particle numbers might change as you add and delete particles from your simulation. So if you want something that doesn't change from frame to frame, you'll want to use the particle ID. The particle ID is fixed for each particle for its entire life. Then we've got something called parent, which records where the particle came from. In this case it's 0 for all of our particles because we've just created them using a location. And then we've got our color attributes, which we've created using this color pop. Now, if I was to move our selection around in a SOP network, you'd expect to see different things depending on which node was selected. In a POP network, however, you see the same view for each of these nodes. So if I select the location node, you might expect the color information to disappear because that is added down here, but in fact it still remains. The reason for that is that a POP network is not really like a SOP network. All of the nodes that make up the network have to be considered as an integrated whole rather than separate steps in a process. It's worth saying a bit about how a particle system evaluates. And the order in which Houdini does things is not completely natural. But what it does first is what's called reaping. That is, it takes all of the particles which are dead or have been killed and deletes the information about them. The next thing it does is look at any acceleration that the particle has and add that to the particle's velocity. It then takes the particle's velocity and adds that to the particle's position to produce a new position, and it thus moves all of the particles according to their velocity and acceleration. It then resets the acceleration value to 0 and evaluates the network to look for any forces that might need to be applied to the particles. And the forces affect the acceleration according to the normal law, which is force equals mass times acceleration. And you can set an attribute on your particles to determine their mass. So every frame it does that sequence of calculations in order to decide where the position of the particle will be at the next frame. Now you might think from that the only way to manipulate the position of a particle is using various forces. But in fact you can manipulate its position directly using a position pop, or you can affect its velocity using a velocity pop, or indeed you can affect its acceleration directly using an acceleration pop. There are also pops that allow you to follow particles, and that will allow one set of particles to follow or approach another. And of course you can set up collisions. And we'll be examining how to use a number of these in the more complicated example that we're going to run through now. But before we do that, let's have a look at the effect we're seeking to achieve. So I've set up the basic scenario here. I've got a sphere, which is going to be the target, which the rays are going to destroy, and it's going to explode. So let's start by setting up an emitter. So I'm going to lay down a geometry node. I'm going to rename it emitter. I'm going to dive inside, delete the file, and lay down a pop network. And the first thing I'm going to do is lay down a location pop. And this is going to be the source of the rays which go and destroy the sphere. So let's have that somewhere down here, like so. Maybe a bit further. And I want the birth rate to be constant, but I don't want it to emit for all time. I'm going to enter a small expression here which tells it to emit particles when the time is less than 2 seconds. And I'm going to emit 20 particles per second. I'm going to create a group for those particles called initial, and I'm going to preserve that group so that this is going to contain all of the particles created from this emitter. Now, on the attributes section, I'm going to reduce the variance to 0. That means that our particles are just going to sit there until we do something with them. The next thing I'm going to do is create another location, and I'm going to call this emit from sphere. And I'm going to go up to object level and take our target, and I'm going to copy these parameters here, its translation parameters. And then I'm going to go back into our emitter, and I'm going to paste copied relative reference, or indeed paste copied reference is probably shorter. So that ensures that these coordinates here match the center point of that sphere. And now I'm going to use and for the birth here, I'm going to make sure that these particles are not going anywhere. I'm just going to birth particles at the first frame, and I'm just going to birth a single particle, and we're going to zero out the constant activation, and I'm going to call this target. And then I'm going to use a follow pop. And a follow pop allows me to move one set of particles towards the position of another set of particles. So let's set up our follow pop. Let's put the display flag on it. And first of all, let's deal with the leader. The leader is connected to this second input here, and so we want to select the group target, which contains the single particle that we've birthed here. And it's fine for the follow pop to aim at the center of that particle. Now I need to set this to normal follow. I don't want the particles accelerating towards their goal. And I want the ambient speed to be 15. And I want them to stop at the leader. So we should now find, and let me just make sure that this is applying only to the points that are being emitted from the location pop. We should find that our particles are being emitted, and we can see here, there they are, they're being emitted and ending up at the sphere. Well, that's a bit boring, the particles just moving in a straight line towards the destination. So let's add some variety. And I'm going to do this by adding some nodes up here between the location and the follow. And for some reason my lines have become straight. I want to have them rounded. I hit the D key there to bring up the display options, then change them to rounded. So I'm going to lay down a force pop, and again I'm going to leave the force at 0, but I'm going to have some noise, and I'm going to reduce the frequency of this down to 0.2, and I'm going to increase the amplitude in the Y and the Z directions like so. So we're going to apply a force which doesn't have a component in the X direction, in other words doesn't have a component which is going to disrupt the flow of particles towards the sphere. And then I'm going to increase the scale of the force to 100. And let's have a look at that. Now we can see that our particles are making a nice curved route through to our sphere, but each of them is being deflected by the same amount. What I want is to have a different noise applied to each particle, and I can do that by offsetting the particle by offsetting the noise by the ID number of each particle times 100, say. That should mean that each particle, and there we are, has a different noise value. The other thing I'm going to do, just to make things a little bit more realistic, is add some drag. And drag ensures that if you have forces in the scene, they don't just accelerate your particles off into the far distance. This applies a countervailing force to the forces that you've applied to the particles, as might happen, for example, if they were moving through water or air. So this should slightly reduce the effect of the noise. So that's produced our particles flowing into our sphere. The next thing I want to do is collide the particles with the sphere. So let's just put down a collision pop. And the collision pop allows you to collide particles with geometry. And we have a choice here of either using parameter values, in other words, choosing by hand the SOP that we want to collide with, or we can use first, second, third or fourth context geometry. Context geometry are the things attached to these inputs here on our PopNet node. Well, we're going to use parameter values, and I'm going to select the target sphere, and then we need to choose what happens when our particles hit the sphere. They're going to die on collision, but I'm going to create an event, hit event. So whenever a particle hits the sphere here, we'll have an event created called hit event. And that should be sufficient for the moment. So let's just have a look at what happens. And we can see that as they hit the sphere, they disappear.